So we're now going to see how to construct a global feature vector f, which maps an entire sentence paired with an entire tag sequence to a vector through these local feature vectors g. And the way we do it is simply to sum up these local feature vectors at the different positions in the sentence. So here I have a sum over I equals 1 to n. N is the length of the input sentence, the length of the tag sequence. I assume that h sub I is the ith history, so the history at the ith position, where I equals 1, 2, 3, 4, 5, and 6. And ti is the ith tag. And I simply sum these feature vectors. So the global feature vector here is equal to a sum of local feature vectors. So, for example, if we take each of these history tag pairs, so g of h1, t1, let's say this has a feature vector equal to this, and then this one might have 0, 0, 0, 1, and then we have 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1. Then f, for this particular word sequence, paired with this particular tag sequence, would be the sum of these feature vectors. So in the first position, I'd sum 1, 2, 3, 4. I have 4 here. Second position, I have 2. The third position, I have 1, 2. In the final position, I have 1, 2, 3, 4. So the global feature vector is formed through a sum of these local feature vectors. Typically, as we've seen in many examples in log linear taggers in this class, and also in the features I gave you earlier in this lecture, typically the local features are indicator functions. They are 0, 1, depending on whether some question about the history in conjunction with the tag is true or false. So for example, G101 might be an indicator function which is 1, only if the current word wi ends in ing and the tag being proposed is vbg. What then happens is that these global features become counts because they are sums of these local features. So the 101th component of our global feature vector, remember we have f is equal to sum I equals 1 to n g hi ti. So it's going to be a sum of these g features applied to every possible position in the tag sequence. In this particular case, f101 is going to be the number of times a word ending in ing is tagged as vbg in this entire sequence. So while the local feature vectors are indicator functions, the global feature vectors are actually counts of different occurrences within the tag sequence. So now when we put things together, we'll see that this way of defining the global features in a global linear model leads to a very convenient property, which is that in spite of the size of gen, remember this is going to be exponential in n, where n is the length of the sentence. In spite of the size of this, we are going to be able to efficiently calculate this function f that takes a word sequence, a sentence as input, and produces a tag sequence as its output. So how does that work? So remember, through a global linear model, this function f is going to be the highest scoring tag sequence. So here I have an argmax over all possible tag sequences in gen, an exponential number of tag sequences. The score within the argmax is v.f, where f is this global feature vector definition that takes an entire sentence paired with an entire tag sequence and returns some feature vector, for example 4, 1, 4, 3, or something like this. Now, if we substitute in the definition I showed you before, this f is going to be a sum from I equals 1 to n of g of hi, ti, where hi is the ith history in this tag sequence, and ti is the ith tag in that tag sequence. So this is, again, just substituting in this definition for f, where we take the sum of these local feature vectors. Now, of course, I can rewrite this slightly, taking the v inside the sum. So the inner product between v and the sum of these local feature vectors is equal to a sum of inner products between v and g, just through some fairly straightforward results from linear algebra. And so this term here can be interpreted as the score for hi in conjunction with ti. So this is basically a score indicating how plausible this particular history tag pair is. So this is the final problem we end up with. We end up with this problem of finding the highest scoring tag sequence, where a tag sequence is scored by a sum of these local scores for each history tag pair in the input. Once we've gotten to that point, it shouldn't surprise you that dynamic programming can be used to find the argmax. In fact, it's a very simple task to modify the Viterbi algorithm, which we originally saw for HMMs, and then we saw for log linear models. It's very easy to modify this to finding the highest scoring tag sequence under these scores.